Hello, let's discuss analysis of indeterminate structures. Now, before going in details, you have to understand fundamental difference between the joints in the structure. There are two types of joints. One is a pin joint, the other one is the rigid joint. Now, if you check, the gray one is the undeformed shape of the truss. Pin jointed structures are mainly the trusses, wherein you don't have any bending moments. You have only axial forces. Now, if you check, this is the gray one is the undeformed structure shape of the structure, and the yellow one is the deformed shape of the structure. Now if you check at the joint, angle between the members after deformation does not remain the same. It may change. Whereas if I go to a rigid frame, then after the gray one is the undeformed shape. This is a typical 2D frame, 1x1 single story height with fixed support here and a roller support here. Now if you check, angle in between the members at joint remains the same after deformation. That is the fundamental difference between a rigid joint and a pin joint. Now what is static indeterminacy? Basically static indeterminacy is divided further internally static indeterminacy and external static determinacy. Addition of the two is the total static indeterminacy. Now if you check what is determinate and what is indeterminate. Determinate is the structure wherein you can find all the internal forces just by using equations of equilibrium. Whereas statically indeterminate structures are those in which you cannot find all internal forces just with the help of equations of static equilibrium. So if you understand, basically static indeterminacy is related to forces. Now there are internal as well as external. So you have to deal with internal static indeterminacy separately and external static indeterminacy separately, because these internal and external are separately required for your force method of analysis. Now additional equations which are required to solve the problem is nothing but the degree of static indeterminacy. So let's go for classification. As I told you earlier, static indeterminacy is related to internal as well as external, or divided into parts. Internal is related to members or forces in internal, whereas external is related to external forces, rather you can say reactions, or related to the support system. So further, if I go in detail, let's analyze a 2D plane pin jointed structure. 2D is nothing but a plane frame or a 2D structure which is pin jointed. Now if you check, let's say M dash are the members which are required to preserve the geometry. Now you all understand triangle is the most stable form or most stable geometry. Now if I say I have J joints in the structure and M as the number of members in the truss. Now if you check, I have a triangle here. Now if you check, first, second and third joint require 1, 2 and 3 members to connect. In addition to that, I have fourth joint. Now if I wish to connect this to my truss, I will have to add 2 more members. Indirectly what it means, for let's say M dash are the initial members required to preserve the geometry, which are nothing but the 3 members. So 3 joints, 3 members. Now how many joints are remaining? Already we have 3 joints. So whatever is the additional joint, for example, I have said that J are the number of joints. So whatever joints remaining are nothing but J minus 3. For every joint, how many members are required? It is 2 members. So if I wish to connect any additional member, I have to add 2 members. Already I have 3 members. So indirectly, if I put this in the form of expression, I will have 3 which are the initial members plus every additional joint, which is nothing but J minus 3, requires 2 members to connect. If we simplify this, you will get degree of internal static indeterminacy equal to M minus 2J minus 3, which is required in your flexibility method, or indirectly we say this force method of analysis. If I have DSI, that is internal static indeterminacy, then you will have to release a member forces, not the reaction. Okay, that is required in force method of analysis. Now if we move forward, that was 2D, now this is 3D. In 3-dimensional structure, pin jointed, if we just closely observe, this is a pin jointed structure wherein 4 joints, 1, 2, 3 and 4 joints require 1, 2, 3, 4, 5, 6 members. Now if I wish to connect another joint, so if I wish to join another member, rather another joint, I will require 3 additional members. Therefore, if I simply put this in the form of m dash, that is number of members required to preserve the geometry, is nothing but 3 members, rather every additional joint requires 3 members to connect. So 3 into j minus 4, because already we have connected 4 joints, plus every additional requires already we have 6 members present in the structure. This is the minimum number of members required to preserve the geometry. Internal static indeterminacy is m minus 3j minus 3. So whatever is excess member in addition to the members required to preserve the geometry are the degree of static indeterminacy. Now let's go ahead. Let's go for the external degree of static indeterminacy. Now it is related to equations. Now if I check, this is the hinge support, this is the roller support. So how many reactions are possible? 3 reactions are possible. So this degree of external indeterminacy is related to only the reactions or external forces, reactive forces. So I have 3 equations of equilibrium available and number of reactions minus 3. Why 3? Because this is a 2D structure, 2-dimensional structure wherein you have 3 equilibrium equations available. So DSE for pin jointed structure is R minus 3. If we add DSI plus DSE, that is nothing but the final degree of static indeterminacy for a pin jointed structure. Now the same if I go for the 3D structure, then available equilibrium equations become 6 because you have x, y, z coordinate. So you will have 6 equations of equilibrium available with you. So DSE for a 3D structure becomes R minus 6. Now that is very fairly straightforward. If you go for a rigid jointed frame, then it is little bit more interesting. If you understand how a structure is called a statically determinate if it is having a rigid joint, it is simple. A rigid jointed frame has to form an open configuration resembling the structure of a tree. Now open configuration here means there must not be any closed loops or cells, and there are additional 2 checks that we have to apply. That is very important. These 2 checks are nothing but if you start from any point and proceeding along any route, you must not return to the same point without retracing the path. That is first condition. Another condition is that it is impossible to make a cut anywhere in the structure without splitting the structure in 2 separate parts. These are the 2 fundamental rules you will have to apply while making cuts in the structure. This is for internal static indeterminacy for a rigid jointed structure. Now if you look closely, this is a typical rigid jointed plane frame. Now if I start, let's say from this red dot I am starting. Now if I start tracing, I will have this loop. Now I can return to this particular point without retracing the path. So what I will do, I will make a cut here such that I will not return back to the same point without retracing. And now I have to retrace. Okay, now we will start from this point. Again I start tracing, then I have a closed loop, which that means I can return to the same point without retracing. So I will have to get this loop also. Now I will start further from this point, this red one. Now again I have started to trace. Now again I am able to come back without retracing, so I will cut this loop as well. Now again I have another point, again I trace. Now this is also possible without retracing, so we have to break this loop as well. Now further we will start with another point, which is the red dot here. Now again I trace. This is also a closed loop, so I will have to break this loop also. Now we have to check, are there any closed loops which we can cut without splitting the structure in 2 parts. As far as I see, it is not possible to cut. I will check. This is the configuration, the yellow one that you see is resembling a tree. Now it is impossible to make any cut in the structure without splitting the structure in 2 parts. That is the fundamental thing. So degree of internal static indeterminacy for a plane frame is 3 times the number of cuts. Why 3? Because you are releasing, when every time you make a cut, you are releasing 3 forces. Which are the 3 forces? You are releasing axial force, you are releasing shear force, and you are releasing bending moment. So these are the three forces that you release each time you make a cut in the structure. So DSI, that is internal static indeterminacy for a 2D rigid jointed frame, is 3 times the number of cuts, or indirectly you can say it is number of loops also. Now if it is the structure has to be resembling a tree, okay, that is the fundamental requirement. So every time you make a cut, you understand first that you must not split the structure in two separate parts. Now that is what it is summarized here. Two forces we release and one moment we release. In 3D structure what happens, you release 3 forces and 3 moments. So it is 6 times the cuts, because you have 3 axes x, y, z. So you release fx, fy, fz, and you release mx, my, mz. So that becomes 6 times the degree of, rather number of cuts that you make. So degree of internal static indeterminacy for a plain rigid jointed structure which is 3-dimensional. It's a typical 3D model of a structure wherein you can see here x, y, z axis. So you are having 6 cut. If you make a cut, you are releasing 6 forces. So that is DSI for a rigid jointed 3D structure is 6 times the cuts, or 6 times the number of loops you have. Now if you just take here, this is a typical example. It is a 3D rigid jointed frame which is nothing but your building. Any building frame is a 3D rigid jointed space frame. Now here I have to cut. Now if you check, we have made how many? As many as 15 cuts, rather 16 cuts in the building, so that the structure becomes open, or in other words it resembles a tree. So degree of static indeterminacy of this structure is 16 times 6. That much is degree of internal indeterminacy for a building frame. Now you can understand why we prefer analyzing a building using kinematic methods, because you have to analyze 16 times 6 forces, that many number of equilibrium equations, or rather additional equations you will have to develop, so that you can solve the problem. So in building frames, normally we prefer kinematic methods or displacements method over force methods. Okay, so we will come back to kinematic indeterminacy, that will clarify your doubts. Now what is the kinematic indeterminacy? It is nothing but the degree of freedom, and in other words, how many additional equations are required to find indeterminate displacement components, as nothing but degree of kinematic indeterminacy. Indirectly you can simply understand it is nothing but the degree of freedom of the structure, or you can understand it how many directions a particular point can move. That is nothing but degree of kinematic indeterminacy. Now if you check a pin jointed frame, now we have seen it already, there is no bending moment in the structure. So each joint can either translate horizontally or translate vertically. In 3-dimensional structure, it can have 3 independent component displacement, which are all translation, x, y, z translation. So if I have now degree of kinematic indeterminacy is nothing but, now if I say degree of kinematic indeterminacy where I have 2 into number of joints minus E. E is nothing but number of available compatibility equation. What is compatibility equation? Now for example, I have a hinge support. At hinge support, no displacements are possible. So that is nothing but the compatibility equation. So Fx here is 0. Rather, displacement in the horizontal direction is 0. Displacement in the vertical direction is 0. Whenever we talk about static, it is related to forces. Whenever we talk about kinematic, it is related to displacements only. So when you think about static indeterminacy, forget about displacement. Consider only forces. When you consider kinematic, forget about the forces, consider about the displacements. Okay, so here E is nothing but number of available compatibility equations. In other words, compatibility, it is nothing but the number of constraints that you impose, that is nothing but the support condition. So I can simply replace E with R, that is nothing but the reaction. So you can simply replace it here and you can find the expression degree of kinematic indeterminacy for a pin jointed structure is 2j minus E. But I would rather suggest you to analyze the structure based on the degrees of freedom at joint. You just visualize what is the possible displacement at every joint instead of using the formula. Same thing if you go for a space frame, you have 3 joint displacements at every joint. So 3j minus e is nothing but the constraint that you impose, because at every joint in a 3D truss you have translation along x, translation along y, translation along z, minus whatever number of compatibility equations you have. Okay, so let's go ahead. Just a second. Now if you have let's go ahead with the 2D. It's very simple. 3D you have to understand. So 3D you have to identify the number of displacements in the coordinates. Now understand, in reality all the structures are 3-dimensional. Okay, so you will have to replace. You can here replace E by R. 3 for 2D, 6 for 3D. Okay. Now special consideration you have to give for inextensibility or extensibility of the member. Now what is inextensible and what is extensible? Now if you consider a building frame, are the dimensions of column and beam allowed to change? Rather, dimension is the span. Can we have change in the span of a column or a beam? Or you can say, in other words, can the height of the column change? No. Can the span of the beam change? No. It is relatively very marginal. So we have to ignore the axial deformations. In other words, these are termed to be inextensible for our understanding. So at every rigid jointed frame, what you have is the joint can have rotations as well as horizontal translations and vertical translation if at all it is there. But if the members are inextensible, for a typical building frame, if I go back, you will see a typical building frame, which is, if I go back, it's at the first slide only. This is a typical building frame. Now if you check, I have 1, 2 and 3 members. Here I have a roller support. Now if you check, if I have members which are extensible, that means every member can change their dimension, or you can say length and height. So this member can change the dimension, so you will have vertical movement I'm saying, not movement. And in horizontal direction you may have separate 2 movements or displacements. Here also a member can displace in the vertical direction as well as in the horizontal direction. So that is not possible in real life structures, or we consider that displacements as very marginal and we simply ignore them safely. So I will have a horizontal displacement which is same for both. That is, in other words, the decay or degree of kinematic indeterminacy, just the independent displacements, not the same displacement, or that you have to consider independent, those displacements which are not the same. Now here if I have one displacement, if now you will see this gray point has shifted to this yellow point, this gray point has shifted to this yellow point, these displacements are exactly the same. So we will have to consider only one horizontal translation, and then these 2 members can rotate, so that is 2 rotations, and this member can horizontally translate and also it can rotate, whereas this is a fixed support, it cannot rotate, it cannot have any degree of freedom, right? So because all 3 degrees of freedom are constrained at the joint. So that way I have only 3 degrees of freedom. If you see displacement method, rather you can see slope deflection method, Carney's method, your moment distribution method, stiffness matrix method, all required to calculate degree of kinematic indeterminacy. So it is nothing but 3 here, 1 horizontal translation and 2 rotations at the joint. Rather it is 3, then this one is 4, and then there is a rotation 5. So there are 5 degrees of kinematic indeterminacy, or 5 degrees of freedom in which direction the structure can displace. If I make this support as fixed, then all 3 again I am constraining, so you will have only 3, which is nothing but 1 horizontal translation because both are the same, and 2 independent rotations. Hope this helps you. All the best. Thank you.